3, we're solving equations. You're probably, if you don't have your unit circle, if you don't remember the memorization of your unit circle, you're probably going to want to have your unit circle handy.
Just don't seem to have as much to lose.
This is on recording. This is awesome.
Strange how the night moves.
Sorry. I love that song, but right now it's time for Bob Seeger to wait. So I'm going to talk first about specific examples, and then I'll move on to talk about how we reason that out for our general answers. In number 1, we're solving an equation. In order to solve that equation, what I'm going to do is I'm going to move the 1 to the other side of the equation. I would then have negative 2 cosine x equals negative 1. If I divide both sides by negative 2 to get the cosine alone, I have the cosine of x equals negative 1 divided by negative 2, which is positive 1/2. And what this is saying is, where is my cosine 1/2? So the specific answers of where your x value, when you take its cosine, is going to be 1/2, would be that your x is equal to pi over 3 in the first quadrant and 5 pi over 3 in the fourth quadrant. That's where the cosine is positive and it's 1/2. Down below it talks about all solutions. And what that means is, as we've talked about earlier in our class, if I'm looking at pi over 3, for example, on the unit circle, I know that that pi over 3 might be located right here. And I can go around the circle and stop at pi over 3, or if I wanted to, I could keep going around that circle and come back to the pi over 3. And I can do that an infinite number of times. So they use symbols to represent that. And what I mean by that is, I could say something like pi over 3, and then if I add on and go around once more around the circle, how much am I adding on? 2 pi. Or 4 pi, right?
Yeah.
Right?
Or 6 pi.
Or 6 pi. Or I can go negative 2 pi. Negative 4 pi, right? I can do all of those. So this is what they do. They do times k where k is an element of the integers. So this k number is a number like 1, 2, 3, 17, 2,334, negative 45. Any integer, positive or negative, that's what the k, the e, and the I are standing for. I stands for the word integers. E stands for the word element, meaning it is a part of the integer group. And k is just any letter. They could have picked p, and it wouldn't matter, as long as they tell you what it is. Now you can say times n, where n is an integer. That's fine too. You can actually write out a sentence if you want to. But in mathematics, this is what they do. This stuff right here, that's highlighted in yellow, is saying go around the circle either direction as many times as you want to. That's the general solution. So the only difference between on the interval and the general solutions is you write down plus 2 pi k, comma or colon or semicolon, kei, which means all the integers multiplied by 2 pi and then added on to what you started with. So then I also, of course, have to talk about the other solution, which was the 5 pi over 3 plus 2 pi k kei. And again, all that's saying is I can go around the circle forwards or backwards, positive or negative, counterclockwise or clockwise, as many times as I want to. That's all it's saying. So this 2 pi k thing is just the generalization, but then you have to tell me what the k is talking about. So in this next one, this is another one that's very similar to the first one. Let's say that in this one, I move my sign to the, I move my sign to the other side. So now the sign comes to the right-hand side. I have 1 equals, if the sign that's positive moves to the right-hand side, it becomes negative. So I have a negative sign already there. And now another negative sign there. That's negative 2 times the sine of x. If I divide both sides by negative 2, I get the sine of x equals negative a half. And what this is saying to me is, where is the sine negative a half? So from my hand trick thing that we learned earlier in chapter 4, I know that those are pi over 6 kind of things. So I'm looking for the pi over 6 things that are in the third and fourth quadrants, because that's where the sine's negative. So in the third and fourth quadrants, those signs are 7 pi over 6 and 11 pi over 6. So those are my two specific answers. 7 pi over 6 and 11 pi over 6. If you're going to do the general solutions, all you would have to do to change it to general is write down 7 pi over 6 plus 2 pi k e I. Again, that's only saying that you're spinning around the circle, because that's 2 pi, as many times as you want to, because you keep ending up in the same spot. And then you would also do that for the 11 pi over 6. So if that's still not making sense to you, one of the important things I learned in math a long time ago, whether we like it or not, is even sometimes if you don't understand, you can still get it right because you know what to do. So make sure you write down plus 2 pi k e I. Okay, that's the big idea. In number 3, when we solve this one, if we get the tangent alone, we'll see that we have the tangent squared of x, which, in case you don't remember, means really the same thing as the tangent of x, the quantity being squared. They didn't want to put the 2 after the x because that means the angle's being squared and not the tangent, so they stuck it in between. And then that would be equal to 3, and that's if I'm moving my 3 to the right-hand side. And then in order to get rid of that square, I'm going to square root. So I square root both sides. Square root the left, square root the right. Oh my goodness, I square rooted a variable, so the tangent of x is equal to plus or minus the square root of 3. Now on your unit circle, if you're looking for that, that's kind of hard to find because they don't give you tangents. They give you the sines and the cosines, right? Cosines first, sines second. But if you use the hand trick, what they're talking about is, where do I have the sine over the cosine end up to be a radical 3? If you remember the hand trick, since we know that we have cosine, sine, tangent being radical 3 is really like radical 3 over 1. And the way you can figure that out, since it's sine for the tangent over the cosine, when you look at your hand trick thing, what you're looking for is the sine thing to be the radical 3. So you bend your finger so that there are 3 fingers to the right of the bent finger. Boom. And that's a pi over 3 angle. And what that means is pi over 3s are the kinds of angles I'm looking for. Which kinds of pi over 3s? Well, you can end up with positives or negatives. If you look in your Cartesian plane, the tangents are positive in the first and the third quadrant, negative in the second and the fourth, but we want them all. We want all of the pi over 3s. So your answers are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And if you check your unit circle and you actually did each of the y values divided by each of the x values, you would find out that in every case you would end up, when you simplify, with a pi over 3. The hand trick is much easier to see, I think. 3 fingers to the right, take the square root of that. That's the sine. Divided by the cosine, divided by 1, that's radical 3. I'm thinking that when I see those 2 cosecants, that maybe, I think I'm going to put them both on the same side. So I'm going to move this cosecant to the left. So that would give me the secant of x, cosecant of x, minus cosecant of x equals 0. And now noticing that I have two cosecants in my brain, I start thinking of the word factor. So I see cosecant in both places, so I factor out a cosecant. And that would leave me with a secant minus 1 equal to 0. Now to me, this, I'm starting to feel better about this already. I see that since I had these two cosecants, that's why I factored out that cosecant. And now what I see is something in my brain that pops up is the zero product property. You guys remember what that was? That means that when you have two things being multiplied, and if you get a 0 on the right-hand side, one of those things has to be 0. Or in other words, either the cosecant of x has to be equal to the 0 you see on the right-hand side, or the secant of x minus 1 has to be equal to the 0 on the other side. One of those two things has to be true. Otherwise, you can't get the 0. If I look at the left-hand side one, and I just talk about that, my brain doesn't work really well with cosecants. Like in my head, I don't see that very well. So I change that. I change it to 1 over the sine and set it equal to 0. Now, in case you don't know, you can never get a 0 as a value unless you can have a 0 on the top of a fraction. Like 0 divided by 7 is 0. 0 divided by 2 million is 0. But if you have 7 divided by 20, that's not 0. 7 divided by a billion, that's not 0. It's really close, but it's not 0. So if you can't get a 0 in the numerator, it doesn't work. So here in this one, there's no solution for the left-hand part. You can't do it. On the right-hand side, if I move stuff over, I would have the secant of x equal to 1. Or in other words, when I simplify that, for my brain at least, I would have 1 divided by the cosine is equal to 1. What does that mean? That means that when you simplify this, like if I multiply both sides by cosine, it's asked me, where is the cosine equal to 1? I hope you know that one. Mason?
Is that 0?
I would take 0, 2 pi. Now, I want to tell you something kind of important, though, in this problem. Take a look up here. Do you see how there's a parentheses around the 2 pi? They're saying 2 pi is not included. So you would have to give an answer of 0. And the moral of the story here in this problem is we did all that for nothing.